அவனை இதனால் இவன் முடிக்கும் என்றாய்ந்து அதனை அவன் கண் விட.
Okay, what exactly thermodynamics deals with? To understand all the mechanism of thermodynamics, we have to be familiar with some variables. They are thermodynamic variables. Okay, what are the thermodynamic variables we are dealing with here in this lesson are: number one, internal energy. Okay, first let us understand internal energy of a system. Let us understand first what is the internal energy of a system, right? Suppose we will consider some gas in some cylinder or somewhat of the closed enclosure containing some gas is there, and the gas molecules I am representing here. These are all the gas molecules. These are the gas molecules. Okay, randomly they are moving, and every gas molecule I am representing the gas molecule as a sphere, and this spherical mass is usually going to be rotating about its self axis. First of all, it is rotating about its self axis. If its radius is r and its mass is m, then the rotational moment of inertia is given by 2 by 5 m r square is the moment of inertia about its self axis. By virtue of self axis moment rotation, it does possess a rotational kinetic energy. The rotational kinetic energy of this molecule is given by rotational kinetic energy is equal to half I omega square, right? I is the angular speed with which the particle is rotating about its self axis. That is the rotational kinetic energy. Okay, and not only this rotational kinetic energy, it does possess some translatory motion. If its speed is v, then by virtue of the translatory motion, the translational kinetic energy is given by translational kinetic energy is given by half m v square is the translational kinetic energy. It is one form of the energy the particle does possess. Okay, and one more potential energy is interactional kinetic potential energy. One more energy is interactional potential energy. Okay, interaction potential energy. This is interaction potential. For example, any two particles are there, gravitational interaction and electrostatic interaction is 1 by 4 pi epsilon naught. Electrostatic interaction energy is given by 1 by 4 pi epsilon naught. If the charge is q square by r is the electrostatic interaction energy. This is the gravitational interaction energy, right? These are all the internal energies of the gas. Okay, one gas molecule does possess these many types of the energies. Okay, and by the way, along with all these things, the particle is under vibration. By virtue of this vibration, it does possess the vibrational kinetic energy and vibrational potential energy also. Okay, the vibrational energy is given by omega square a square. A square is A is the amplitude of oscillation. This is vibrational energy. Vibrational energy. These are all various types of the energies: rotational kinetic energy and translational kinetic energy, and interaction gravitational potential energy, interactional electrostatic potential energy, vibrational energy. These are all the various functions, and all these types of the energies are possessed as a function of temperature. Okay, if I take the temperature of the body at any instant, temperature of the body is equal to something like T, then energy at temperature T is given by F by 2 N R T, where F is the degree of freedom. F is the degree of freedom, and N is the number of moles, right, and R is the constant, universal constant, and T is anyway, it is a temperature. Okay, so you can see the internal energy of the gas is the pure function of temperature. That means from this you can say interaction energy is directly proportional to temperature. That means if temperature increases, the internal energy of the gas increases. If temperature change is delta T, then internal energy also will be changed proportionally according to temperature. That means the change in the internal energy is given by F by 2 NR into delta T. Okay, and here you can also write Fr by 2 as N into Fr by 2 into delta T. Okay, where Fr by 2 is called CV. CV means molar specific heat of the gas at constant volume. I'm writing it. It's very important parameter of the thermodynamics chapter. This is molar specific heat of gas at constant volume is called CV, right? So the change in the internal energy can be written as NCV delta T. Okay, and if molar specific heat of the gas at constant volume is CV, and based on this you can define molar specific heat of the gas at constant pressure as well. Okay, so what is the molar specific heat of the gas at constant pressure? That's what I am giving you here. Molar specific heat of the gas, specific heat of gas at constant pressure, constant pressure, Cp, constant pressure, Cp is given by Cv plus R. And what is the Cv? This is Fr by 2 plus R, and that is equal to F by 2 plus 1 into R. And the adiabatic constant, the ratio of Cp and Cv is called this constant has a specific role in the chapter thermodynamics. That's why gamma is called thermodynamic constant, and is given by, it is adiabatic constant, and that is equal to Cp divided by Cv is equal to, what is the Cp? F by 2 plus 1 into R divided by Cv is Fr by 2. Okay, and you, by dividing these two, we do get R get cancelled, and this can become equal to F plus 2 divided by 2 whole divided by F by 2, right? So to again simplify, these two get cancelled, and what are the remaining things you write here? That will be F by 2 plus 2 by F can be written as 1 plus 2 by F. Okay, like this You can understand the ratio of Cp and Cv. Okay. According to the atomicity, the degree of freedom is different from one type of the gas to another type of the gas. Okay. So for according to the atomicity for monoatomic gas, the atomicity is for monoatomic gas, monoatomic, diatomic, di means two, diatomic, and polyatomic gases. Polyatomic gas will take. Then for these gases, what is the value of the degree of freedom? We will see. The degree of freedom for monoatomic gas is 3, and for diatomic gas it will be 5, and for polyatomic gas it will be 6. Okay. And according to this degree of freedom means in ordinary cases, the degree of freedom is nothing but, this is nothing but, F is nothing but called degree of freedom. I'm writing it here, degree of freedom, degree of freedom. Okay, what exactly the degree of freedom is, let us understand. Okay, degree of freedom, let it be written simply by the letter F. Okay, usually by virtue of translatory motion, by virtue of rotational motion, by virtue of vibrational motion, this degree of freedom will be defined. Okay, by virtue of translational degree, for according to the atomicity, it changes from one gas to the another gas. The atomicity point of view, the gases are divided into monoatomic gases and diatomic gases and polyatomic gases. Monoatomic gases means the translational degrees, degree of freedom F at ordinary temperature. For monoatomic gas it will be 3. 3 means all the three are translational degrees. Translational degrees, all the 3 degrees are translational degrees, and rotational degrees are 0. There is no rotational degrees for monoatomic gas. No rotational degrees. By virtue of rotatory motion, there is no degree of freedom. That means a degree of freedom, what exactly the degree of freedom is? The number of possible ways in which an atom or a molecule can possess the energy is called the degree of freedom. The number of possible ways. Only by translational motion point of view, the molecule does possess the energy in the case of the monoatomic gas. That's why there is no rotational degrees. No rotational degrees in the case of monoatomic gas. Whereas you come across the diatomic gas, the situation is different. The number of degrees are 5. Out of 5 degrees, 3 degrees are translational degrees. Translational degrees are 3. And rotational degrees are 2. 2 are rotational degrees. Okay, total number of degrees will be 3 plus 2 will be 5. Okay, for diatomic gas. Whereas come across the polyatomic gas, total number of the degrees of freedom are 6. That means out of 6, 3 translational degrees, 3 translational degrees, and another 3 are rotational degrees. 3 rotational degrees, right? So like this, from one gas to the other gas, it changes like this. So far as degree of freedom is concerned, for monoatomic gas, degree of freedom is 3, diatomic gas degree of freedom is 5, polyatomic gas degree of freedom is 6. If there are some exceptional condition of the gas, at very high temperature, just like that in stars, in sun, LCS, Sirius, like that in the stars, the temperature is of order of thousands of the Kelvin. Then what happens? The situation of the molecule is concerned, it is in vibration state with a larger and larger amplitude, and thereby 2 degrees will be added at very high temperature, very high temperatures. At the 2 more degrees will be added. So 3 plus 2 at very high temperatures, exceptional degrees they are. 3 plus 2 equal to 5 degrees are there for monoatomic gas, and 2 equal to degrees are there for diatomic gas, and 6 plus 2 is equal to 8 degrees are there for polyatomic gases. Okay. And diatomic, polyatomic means you can understand a molecule, one molecule itself, one atom itself existing as a molecule is called monoatomic gas. Two atoms combinedly exist in the nature for availability, they are diatomic gases. If three or more than three molecules exist in nature to come to availability are called polyatomic gases. Okay. So for these many different types of the gases, the degree of freedom at ordinary temperature in the questions, if it is not specified whether it is there at the higher temperature or not, then we have to usually take ordinary degrees, right? These are all monoatomic 3 degrees, diatomic 5 degrees, polyatomic 6 degrees are called ordinary degrees. Exceptional degrees at very high temperature, just like the temperature of the stars are concerned, the 2 degrees, one is the potential energy, other is the kinetic energy, right? These 2 degrees will be added to the additional degrees, and that's how you will get for monoatomic gas 3 plus 2 5, for diatomic gas 5 plus 2 7, and for polyatomic gas 6 plus 2 8 degrees are to be taken into consideration. Based on this degree of freedom, we can define the molar specific heats at constant volume and at constant pressure, right? So now, so far as CV is concerned, what is the CV? Molar specific heat of the gas at constant volume, and its formula we have already taken it as a FR by 2, and for monoatomic gas, its value will be, for monoatomic gas, the value will be, what is the degree of freedom? 3. So that will be 3R by 2, right? And CP, what is the CP value? What is the formula for CP? CP is equal to FR by 2 CV plus R. This is called Mayer's equation, that is equal to FR by 2 plus R, right? So 3R by 2 plus R will be 5R by 2 at ordinary temperature, right? At very high temperature, I am not writing, I am not specifying in this slide. You can apply them whenever in the questions, in any question exceptionally they have specified that exceptional degrees are taken, that is at very high temperatures, right? This is the way you can find CV, CP. And so far as the gamma, the ratio of CP and CV is concerned, CP by CV is equal to gamma, that is equal to 5R by 2 divided by, and also we know in the previous slides we have seen the expression for the gamma as 1 plus 2 by F. So this is what of the expression 1 plus 2 by F we can specify. If you substitute the degree of freedom for monoatomic gas 3 here, you will get 5 by 3. The gamma is equal to CP by CV. Of course, it will be 5 by 3 for monoatomic gas. Okay. So what is the CV value, and what is the CP value, and what is the gamma value? This is what you can see here in this slide. In the same way, if you go for a diatomic gas, what is the degree of freedom for diatomic gas? It will be 5. You just substitute the 5 in the formula. CV is equal to FR by 2. For diatomic gas, it will be 5R by 2 is the CV, and for CP, it will be 5R by 2 plus R. R should be added for CP. This is the molar specific heat of the gas at constant pressure. So this will be 7R by 2. And gamma is equal to CP by CV, and dividing these two, you will get 7 by 5 is the gamma value. And in the same way, if you go for a polyatomic gas, what is the situation in the case of the polyatomic gas? What is the degree of freedom in the case of the polyatomic gas? Polyatomic gas degree of freedom is how much? That is 6. So CV will be 6R by 2 and also can be written as 3R. And for the same polyatomic gas, it will be 6R by 2 plus R will be 8R by 2. 8R by 2, or this can also be written as 4R. And gamma is Cp by Cv. If you divide these two, the ratio can be taken as 4 by 3, right? And you can observe the monoatomic gas, diatomic gas, and polyatomic gas, the Cp-Cv ratios. You observe these values. What is the value of 5 by 3? This will be 1.3 and 367. 1.67 is the gamma value for monoatomic gas, and the gamma value for polyatomic gas, diatomic gas, it will be 1.4, and that for the polyatomic gas, this will be 4 by 3. 4 by 3 means how much? 1.33. You see what happens to the adiabatic ratio, gamma? It is decreasing with increase in the atomicity. Okay, so this logic you can remember here. Okay, so the gamma value decreases with increase in the atomicity. Okay, gamma is adiabatic ratio. This is a very important statement. I am writing it here. The value of gamma is decreasing with increase in atomicity, right? So gamma, the ratio of Cp-Cv ratio is decreasing with increase in the atomicity, right? Okay, right. Now we will go for, we have come across, we are coming to know the internal energy of the gas first of all. Okay, so we'll go to the actual topic of this lesson is internal energy of the gas. So already we discussed that internal energy of the gas is a pure function of temperature, and that is nothing but given as NCV T. T is the temperature. It is at T temperature, the internal energy is NCVT, and the PV again be written as FR by 2. Okay, and if the temperature is changed, change in the internal energy is given by NCV into delta T. Delta T is the change in the temperature, right? If the temperature is increased, internal energy increases and vice versa. Okay, so internal energy is a pure function of temperature, whatever the process that may be. It may be a constant pressure process, or it may be a constant volume process, constant temperature process, or any system. The internal energy is calculated according to this relation. Okay, this is only the relation we are using in any process to calculate the change in the internal energy, right? Now we will see another parameter of thermodynamics, that is external work done. We will see external work done. What is the external work done? To understand the external work done against a constant pressure, some setup I am going to take. For that, let me consider a piston-like arrangement here, and it is a cylindrical-like arrangement. And in this cylinder, it is a closed cylinder. Of course, both the bases are closed, and here is some orifice to equip a horizontal pipe. Some horizontal pipe is here, and in this horizontal pipe there is a movable piston. There is a movable piston is here, and this in this a gas is taken. The gas molecules are like this, and the gas molecules are taken in the cylinder, and all these gas molecules are there, are possessing the internal energy anyway, and the internal pressure at any instant is, say, P is the pressure. The P is constant throughout at every point. Here also the pressure will be P. And let us suppose the area of cross section of the piston, which is in contact with the gas, is P is the pressure, and this area of cross section, let me say this is A, right? And because of this pressure, if the piston is smooth to move, there is no friction that is acting between the piston outside walls and the cylinder inside walls. Then piston is supposed to be moved away by the friction, right? After some time, let us suppose the piston has come to a new position, somehow like this. Somewhat new position is attained by the piston, right? For suppose x or dx, small distance I will consider, dx, some differential distance that is moved away by the gas, right? Because of this, what happens, volume is increased. What is the change in the volume? First let us calculate the force that is acting on the piston, right? What is the force that is acting on the piston is concerned? This gas is offering a force F here, and that F is a pressure into normal area of cross section is the force. So that force is given by pressure into normal area of cross section. Okay. If this force is acting constantly, then if the pressure is constant, the force will be constant. Then work done in making the displacement to dx is given by dw is equal to F into dx. You substitute the value, the formula for the force as P into A into dx. What is A into dx? The product of A and dx is nothing but change in the volume. Okay, so this is the volume that is additionally occupied by the gas. Okay, so the A into dx is taken as the change in the volume. This is a change in the volume, right? I'm going to write the change in the volume here, that is P into change in the volume, or dV. P into dV is the change in the volume. Okay, so additional work done or external work done is given by P into dV, right? These two are the two thermodynamic variables we have to understand to proceed into the lesson. Okay, now let us understand the first law of thermodynamics. Okay, actually there are three laws in thermodynamics. The very three laws are, the first thing is zeroth law of thermodynamics, law of thermodynamics. And the second thing is first law of thermodynamics, first law of thermodynamics, and the second law of thermodynamics. The third law is second law of thermodynamics. Okay, so for today let us concentrate on the zeroth law and first law. What is the zeroth law? Zeroth law says about the internal energy and temperature. What zeroth law says means it is very simple. For example, if any two systems we consider, One system is the system A and the other system is the system B. And A and B are in thermodynamic equilibrium. Thermodynamic equilibrium, what is thermodynamic equilibrium? Let us have to understand. That means if no heat exchange takes place between A and B, that means both are at same temperature. That means the temperature of A is equal to temperature of B, right? Then the two systems are said to be in thermodynamic equilibrium. For example, if any third system we take into consideration, some third system C I will take, and if this third system C is in thermodynamic equilibrium with A and with B separately, then A and B are said to be in thermodynamic equilibrium. That is the zeroth law. Okay, zeroth law of thermodynamics. What zeroth law says? If any system C is in thermal equilibrium with A and B, two different systems separately, then the two systems A and B are said to be in thermodynamic equilibrium. This is the statement of zeroth law. Okay, the zeroth law mainly says about the temperature and internal energy of the gas. What is the internal energy? We have seen in the previous slide. That is by virtue of translational motion, by virtue of rotational motion, by virtue of vibrational motion, by virtue of the interaction between one gas particle and another gas particle, right? So by these many ways, a gas does possess the energy. That's all called internal energy of the gas. Okay. And zeroth law says about that internal energy. Being the internal energy is a function of temperature, zeroth law explains the temperature. Now let us come to first law of thermodynamics. Okay, what first law says? Let us understand here. First law of thermodynamics. First law of thermodynamics. First law of thermodynamics. Okay. What first law says? If you consider any system, some system is there, and in this system there are gas molecules. Okay, and out of this system, other than this system, all the surrounding is, other than this system, all the rest of the part is called surrounding. I am writing it here. This is surrounding. Okay, there will be a continuous interaction between, this is the system, this is the system, and other than the system, all the rest is taken as a surrounding. There will be a continuous interaction between the system and surrounding. The system particles and surrounding particles are in interaction continuously. Okay, because of this interaction, some changes will take place in the system. What are the types of the changes and how the changes are going to be taking place, and what are the consequences of all the changes? That is all the study of thermodynamics now. Okay, so the system, from surrounding to system, some heat energy may be communicated. That means if the heat energy is supplied from surrounding to system, that surrounding to system, the heat energy supplied is delta Q. That delta Q is doing two functions. One is to raise the internal energy of the gas, and other is to do the external work, right? So that's why it the first law of thermodynamics can be formulated and be written as delta Q is equal to delta U plus W, is the very fundamental form of the first law of thermodynamics. And delta U, you know very well that the delta U is increase in internal energy, increase in internal energy, and W is the external work done, right? This is what the first law of thermodynamics says. And the system and surrounding is separated by a boundary. The boundary, which type of the boundary, that is a separating system and surrounding, based on the type of the boundary that is separating the system and surrounding, we can differentiate the different types of the systems here. Okay, different types of systems based on type of the boundary separating system and surrounding, right? Okay, so system and surrounding are separated by a boundary. Okay, there are basically three types of the boundaries. They are open system, closed system, and isolated system. I'm writing them here. Types of systems can be recognized as open system, number 2 closed system, and number 3 isolated system, right? What is the open system, what is the closed system, and what is the isolated system? Let us see. Open system means between the system and surrounding, both heat and matter exchange takes place. In the closed system, only heat exchange takes place, but matter exchange will not takes place. Isolated system, neither heat exchange takes place nor matter exchange takes place. Okay, so like this, the systems are of three types based on the type of the boundary. Open system, in the case of the open system, heat exchange and matter exchange, both exchanges takes place between system and surrounding. In the case of the closed system, only heat exchange takes place between system and surrounding, no matter exchange takes place. Isolated system, nothing will change, nothing exchange takes place. That means neither heat energy nor matter will take place between system and surrounding. Okay, so these three are different types of the systems, right? Now, based on the type in which a system, in the system, what exactly is there inside the system? There are some gas molecules, yes or no? Some gas molecules are here, and the gas molecule, the state of the gas molecule is measured in terms of pressure. Number 1, pressure, and number 2, volume, and number 3, temperature, right? So what is the pressure, what is the volume, what is the temperature, and what is the internal energy as well? Of course, internal energy is a pure function of temperature. That's why I'm not specifying that as a different parameter to state the status of the system, right? So depending upon PVT, you can say in what condition the system is. If, for suppose, pressure may be changed, may be changed, volume may be changed, temperature may be changed, any change in any parameter, that change takes place is called a process. What is the process? The change change in either pressure, volume, or temperature, or change in all the parameters. That is called a process. Okay. Based on the type of the processes, there are so many types of the processes are there. They are constant pressure process, there are constant volume process, and there's constant temperature process, and isolated system process. Like that, different types of the processes are there. Okay, so we will consider the processes one by one here. And all these processes, that is the study of all these processes, is nothing but called the thermodynamic processes. Okay, and in these thermodynamic processes, we are going to study the special cases here. The first thing, very first thing, is constant temperature process. Constant temperature process is also called isothermal process. Isothermal process. In the isothermal process, temperature is constant. If the temperature is constant, then change in the temperature will be zero. If temperature is constant, internal energy of the system is NCV into T is constant, and change in the internal energy will be NCV delta T. Being delta T is zero, change in the internal energy also will be zero. Right. So according to first law of thermodynamics, from first law of thermodynamics, we can say delta Q is equal to delta U plus external work. Being delta U is zero in the case of the isothermal process, entire heat energy, 100% of the supplied heat from system to surrounding or surrounding to system is doing only external work. That means external work will be maximum will be extracted in the case of isothermal process. Being temperature is constant, this process also called Boyle's law. Right. What according to Boyle's law, what you know? Boyle's law, PV is constant. In the ideal gas equation, PV equal to nRT. N is the number of moles, and R is the universal gas constant, and T is the temperature. Being N is a constant, R is a constant, T is a constant, the entire process can be recognized formulatedly as PV is equal to constant. So P is inversely proportional to volume. That means if you draw a graph between pressure versus volume, say pressure is taken along the y-axis and volume is taken along the x-axis, it is a rectangular hyperbola. How do you get the curve between pressure versus volume? This is a rectangular hyperbola. Okay, PV graph. This is called PV graph. If temperature is increased, process at T1. If the temperature is increased, then that graph is going to be, sorry, this graph is going to be obtained somewhere here. This is another isotherm. Okay, this is at temperature T2. Okay, so if two isotherms are given like that, then T1 is greater or T2 is greater from the origin. Whatever the process is farther from the origin, that particular temperature is said to be large. So from this graph, you can understand that T2 is greater than T1, right? So the higher temperature isotherm will be farther distant away from the origin. That is isothermal process. In the isothermal process, you can also say PV equal to constant. That is according to ideal gas equation, and P is inversely proportional to volume. If you consider two different states, then at one state the pressure will be P1 and volume will be V1. This is the pressure and volume coordinates are V1 and P1, let us say, and after some time the same process, the same gas has come to a volume V2 and its corresponding pressure P2. Then according to this relation, P is inversely proportional to volume, you can write it as P1 by P2 is equal to V2 by V1, right? So PV is equal to constant. This is what of the formula also you can get. Now let us calculate isothermal work done. And in the case of the isothermal process, being internal energy is constant, what is the specific heat? Temperature of the gas is constant here. And you can also write according to the specific heat. What is the specific heat in isothermal process? Actually, any delta Q is given by M S delta T. S is the specific heat process, and also of course, let me write the specific heat in isothermal process as C. Then C is equal to delta Q divided by M delta T. What is the delta T value in the case of isothermal process? Being temperature is constant, delta T will be 0. That's why the specific heat is equal to infinity. That means as much amount of the heat you supply from surrounding to system, its temperature never ever gains. Okay, so infinity is the specific heat in isothermal process. Okay, and also let us have to calculate the isothermal work done. Okay, so already in the previous case we have discussed the way of calculation of the work done. The dW is equal to let me take P into dV, right? And from ideal gas equation, what you know, PV equal to nRT equation, you can write the P as the P is equal to nRT by V, right? So instead of the P, let us substitute that value, that will be nRT divided by V into dV is the work done. And now this work done, let it be taken with appropriate integrals on both the sides. Okay, so integral dW is given by W, isothermal work done is given by, and let me suppose the volume limits are from V1 is the initial volume, V2 is the final volume, and being temperature is constant, all the numerator is constant, and let it be written outside the integral operator, and it can become nRT into integral 1 by V into dV in the limits V1 to V2. So what is 1 by V dV? It is a natural logarithm, right? nRT, natural logarithm ln of V in the limits V1 to V2, right? And you substitute the limits here, that will be nRT into ln V2 minus ln V1. Okay, and ln V2 minus ln V1 is written as nRT into ln V2 by V1. And in terms of the pressure also it can be written according to the process equation. What is the process equation here? The process equation is PV equal to constant, that is P1 V1 is equal to P2 V2, right? So being it is P1 V1 equal to P2 V2, 1 minute, I'll write it once again. P1 V1 equal to P2 V2, and how can you write V2 by 2 P1 by P2? Okay, so the isothermal work also be written, this is one form. In terms of the volume it can be written like this, and in terms of the pressure the isothermal work can also be written as, the work done also be written as nRT into ln natural logarithm is exponent P, okay, 1 divided by P2. This is also a isothermal work done. Okay, right? and it is in natural logarithm, that is exponential logarithm. In the decimal logarithm, how can you convert the natural logarithm into decimal logarithm? To convert that, this will be turned to 2.303 nRT ln V2 by V1. Okay, and the same thing also be written as 2.303 nRT ln P1 by P2. Okay, this is the way you can get the expressions for the isothermal work done. Okay, so the very basic points you have to remember regarding the isothermal work done is temperature is constant. Isothermal process, temperature will be constant and change in the temperature will be zero, and therefore the internal energy is constant, change in the internal energy will be zero. And according to first of thermodynamics, being changed, first of thermodynamics says the heat supplied is a sum of internal energy change and external work, and being internal energy is constant, change in the internal energy will be zero. So 100% of the heat supplied will be converted into external work. And so being it is temperature constant process, this process also called obeying the Boyle's law, and so it will be given as PV equal to nRT, or P is inversely proportional to volume, and isotherms at different temperatures of the given system of gases are given like this by means of rectangular hyperbolas. Then P1 by P2 will be V2 by V1, and delta Q equal to MC delta T, and C is delta Q divided by M delta T. Being delta T will be zero, then specific heat of the process is taken as infinity. Okay, and the work done dW is given as P into dV, and this is what of the calculation already we have seen in the initial stages of the thermodynamics there in the very beginning slide. Then in taking the integrals, it will become W equal to nRT 1 by V dV. With the help of ideal gas equation, you can write it like this, and the isothermal work done can be given as nRT into ln V2 by V1, and W is 2.303 nRT into ln V2 by V1. And in the case of the decimal logarithms, this can be written in terms of the natural logarithm or decimal logarithm. It is not ln, I'm sorry, this will be decimal log. This is log V2 by V1 to the base 10. It will become the base will be log here, no more ln. Decimal log means base is 10, exponential log means base e, the value of e is 2.7. So okay, and now let us go for one more process here, that is iso constant pressure process. What is the constant pressure process? Let us see. That is also called isobaric process. Let us see. Isobaric process. What is the isobaric process? In the isobaric process, pressure is constant. Pressure will be constant. Okay. Against the constant pressure, you can write the first law of thermodynamics now. From first law of thermodynamics, what you know? The heat supplied to delta Q is equal to change in the internal energy delta U plus work done. Of course, external work done. And that is equal to delta Q can be written as NC delta T. Being it is a constant pressure process, the C is Cp and delta U is NCV delta T plus external work done is P into delta V, right? Being pressure is constant in the indicator diagram, you can get pressure is constant if you take the process graph, the graph of the process, you take the pressure along the y-axis and volume along the x-axis. Being pressure is constant, the graph is perpendicular to the pressure axis. That means between two different volumes, you consider this is the volume point V1 and this is the volume point V2. Between V1 and V2, whatever the area of the graph that is bound here, the area of PV graph with the volume axis will give you the work done. Okay. So it is clearly representing a rectangle. This rectangular area is giving you the work done. Okay, isobaric work done. Okay, so that's why the work here can be written as P into delta V, P into V2 minus V1. That is also P into delta V. Okay, being it is a constant pressure process, the work done can be calculated like this. And P into delta V, how do you write P into delta V? That will be PV2 minus PV1. How can you write PV2? nRT2 minus nRT1. Okay. And if you take nR into T2 minus T1 is delta T, nR delta T. Okay. And if you write the P into delta V value, also I will substitute it here into the convenient form. That is NCP delta T equal to NCV delta T plus NR delta T. Now both sides you simplify it. What do you get? N will be cancelled and delta T also will be cancelled. Then what do you get? Cp is equal to the Mayer's equation you are getting here. You see Cp equal to Cv plus R. So the Mayer's equation is nothing but constant pressure process or isobaric process for 1 mole of the gas. Okay. So Cp represents molar specific heat of the gas at constant pressure, and Cv represents molar specific heat of the gas at constant volume, and R represents the work done on 1 mole of the gas. Okay, this is the isobaric process. In the case of the being pressure is constant, if you take the graph between volume and temperature, right? In from ideal gas equation, you can get from ideal gas equation, you can write it as from PV equal to nRT. Here, the pressure is constant, N is a constant, R is a constant. So, what is remaining now? This implies volume is directly proportional to temperature, right? That means V1 by V2 equal to T1 by T2. Okay. So, if you draw a graph between volume versus temperature, volume versus temperature, if the temperature is in Kelvin scale, then the graph passes through the origin. If the temperature is in a degree centigrade scale, if the temperature is in Kelvin scale, right? If the temperature is in degree centigrade scale, is somehow like this: volume versus temperature graph is somehow like this, right? And it will touch the x-axis or temperature axis at minus 273 degrees centigrade, right? The temperature is taken in centigrade scale, right? Okay, so here these are the various aspects, and also we may get here that the temperature, for example, here is the pressure P1 and here is the pressure P2, right? The graph volume and temperature at pressure P1 is at pressure P1 is like this and P2 is like this. P1 is greater or P2 is greater? Which is greater? How can you say, right? So if you go for that analysis, you go for a constant temperature process. You take a reference line, what are the reference line, you take constant temperature, up volume values are there, the P1 corresponding volume is V1 and P2 corresponding volume is V2. Okay, so V2 is greater along the y-axis. V2 is greater, so at constant temperature pressure must be less according to isothermal process. Yes or no? So that's why V2 is greater, that's why P2 is lesser. So you can say easily P2 is less than P1. This is what of the analysis also you can do regarding the isobaric process. And so far as the specific heat is concerned, what is the specific heat? So delta Q, to get the specific heat, you have to take delta Q equal to ms delta T, mc delta T, and can m is the mass of the gas, is the specific heat. Specific heat is delta Q divided by m delta T. And what is the delta Q? Here already you wrote it. Now n Cp delta T, instead of the n you can also write m Cp delta T. So the specific heat is Cp here. Of course m delta T will be cancelled. The specific heat in the isobaric process, C equal to Cp. Okay, so these are the various results you have to remember regarding the isochoric process. In the isochoric process, volume will be kept constant. Being volume is constant, change in the volume will be zero, right? Being change in volume zero, what is the external work done? The system volume is constant, so there is no change in the volume system, right? So therefore external work done, external work done will be integral P into dV. What is the dV here? The dV value is 0. That's why external work done will be 0. Okay, no external work. If no external work, you see this according to first law of thermodynamics. From first law of thermodynamics, first law of thermodynamics, it can be written as delta Q equal to delta U plus external work. Being external work is 0 in this case, the delta Q is 100% of the delta Q is utilized for increase in the internal energy. That is, increase in the internal energy is nothing but N Cv delta T. Okay, Cv is the molar specific heat of the gas at constant volume. Okay, and Cv, different forms of the Cv already we discussed, that can be written as FR by 2. For monoatomic gas, F value will be different, and for diatomic gas it will be different. For monoatomic gas it will be 3, for diatomic gas it will be 5, and for polyatomic gas it will be 6. Like that you can get a Cv value differently there. And also this equation may also be written as F by N, that value I am taking it here like this. This can be written as R by 2, F by 2 into Nr delta T. Nr delta T. If temperature change is from T1 to T2, this can be written as F by 2 into Nr into T2 minus T1. Now this can be written as F by 2 into Nr T2 minus Nr T1. Okay, so that is equal to F by 2 into nRT2 is P2 V2 minus P1 V1. Okay, this is also another expression. These are all various expressions to calculate the internal energy change, right? So this internal energy change can be applicable in any process. It may be isothermal process, it may be any adiabatic process, or it may be a isochoric process or isobaric process. In all the processes, the way of calculation of change in the internal energy will be same. But in the case of the isochoric process, according to first law of thermodynamics, we know that delta Q is completely 100% is utilized only for increase in the internal energy only. Okay, this is what of the point you can remember regarding the isochoric process. And by the way, you being the volume is constant according to ideal gas equation, this can also be written as from ideal gas equation, you can also write it as PV equal to nRT formula. From PV equal to nRT, from ideal gas equation, PV equal to nRT, what is constant? Volume is constant, right? And nR is any pressure is directly proportional to temperature, right? Being pressure is directly proportional to temperature, P1 by P2 can be written as P1 by P2 is equal to T1 by T2. If you analyze this process graphically, and thereby you take volume pressure along the y-axis and temperature along the x-axis, and you may get a proportionality graph here. Here also you can say if the temperature is in Kelvin scale, the graph passes through the origin. If the temperature is, for example, I will take one more graph here. If the pressure versus temperature graph is in degree centigrade temperature is there, right? Then the graph is not passing through the origin. It is a straight line, of course, but it touches the temperature axis at minus 273 degrees centigrade. Okay, 0 degree centigrade is here, and it is the 0 degree Kelvin, 0 Kelvin, right? So usually in all these formulas, we are taking the temperature only in Kelvin scale, not in the degree centigrade scale. In case in any problem, if it is given in degree centigrade scale, you have to convert it into Kelvin scale. How do you convert degree centigrade into Kelvin scale? Plus 273. If you add 273, it will be converted into Kelvin scale, and Kelvin scale values should be substituted in the equations and go for further simplifications, right? So regarding the isochoric process, you have come across the various aspects. Here volume will be constant, change in the volume will be zero, external work done will be zero. That's why according to first law of thermodynamics, delta Q equal to delta U plus W, and being the W is completely zero here, 100% of the delta Q is spent only to raise in the internal energy of the system. So delta Q here, the process, in this process, the specific heat of the process also very important here. The specific heat is Cp. What is the specific heat? C equal to Cp, not Cp, Cv is the specific heat. Okay, this is the isochoric process. Okay, and other than the isochoric process, let us see there is neither heat exchange nor matter exchange takes place between the system and the surrounding. One system is there in the types of the system based on the type of the boundary which is separating system and surrounding. We have classified the systems into three types. Previously we have seen that. That's why in the case of the isolated system, we are conducting the adiabatic process, and let us see the details of the adiabatic process now. Okay, what is the adiabatic process? Adiabatic process. Adiabatic process. In the adiabatic process, the adiabatic process is done only in the isolated systems. What is isolated system? First of all, what is isolated system? In the case of isolated system, delta Q, that is heat exchange between system and surrounding, will be zero. So from the first law of thermodynamics, from first law of thermodynamics, you know delta Q is delta U plus W. Being delta Q is completely zero, zero is delta U plus W. That means the external work done is minus delta U, or delta U is equal to minus W. That means if volume expands, the work done will be positive. I am giving you the sign conventions for work done: positive, negative, internal energy positive and negative here. Okay. What are the various sign conventions? They are very important here. Okay. So sign conventions are given as: if volume expands, delta V is positive. Volume contracts or decreases, volume contracts, delta V is negative. Okay. Temperature increases. Then if volume expands, delta V positive, then automatically W also will be positive. If volume contracts, delta V will be negative, then automatically W will become negative. Okay. So like this you can say, if volume expands, work done is taken to be positive. If volume contracts, work done is to be taken with a negative sign convention. Okay. And the temperature conventions also, let us see. The temperature conventions are: if temperature increases, then delta T is taken positive. If delta T is positive, change in the internal energy also positive. Okay. Otherwise, if temperature decreases, or reverse happens, temperature decreases, then delta T will be negative, and delta U also negative. Yes or no? So work done, no temperature. You see here, minus negative internal energy means, and positive work done. What does it mean? Positive work done means what happened? Volume is expanded and temperature is decreased. So this graph, this is indicating you that W positive means volume is decreasing, and volume is increasing. Volume is increasing, and temperature, internal energy is, what is the internal energy? Internal energy negative means temperature decreases. Okay. And you see this one, delta U is positive here. That means delta U represents the temperature. Temperature increases. And work done negative here. Work done negative means what happens? Work done represents the volume. Volume is decreasing. Okay. These are the conventions we can follow here regarding the adiabatic process. Okay. So, and in adiabatic equations also there, let us have to find the adiabatic equations. What are the adiabatic equations? Let us see now. Okay. What is the adiabatic equations? Adiabatic equation. We will see. The first equation is the relation between pressure and volume. That is, I will explain you in detail in the next sessions. P V power gamma equal to constant. where gamma is called adiabatic constant. Gamma is, since gamma is Cp by Cv. What is the Cp by Cv? All these values we have already discussed. Okay. And you differentiate this equation. What do you get? P dP into V power gamma plus P into gamma V power gamma minus 1 into dV equal to 0. That implies you take V power gamma constant common, dP plus P gamma into V power minus 1 into dV equal to 0. Shifting the V power gamma to that side, it becomes dP is equal to minus P gamma divided by V. I am writing V power minus 1 like this by dV. And you know dV by V. This can be given as, this implies dP divided by minus of dV by V is equal to gamma P. This is called adiabatic bulk modulus. Adiabatic bulk modulus means dP is called the stress, bulk stress, right? And dV by dV is called bulk strain. Okay, what is the ratio of stress to strain is called bulk modulus. Okay, so that's why it is called adiabatic bulk modulus. Adiabatic bulk modulus. Whereas in the case of the isothermal process, if you see, in case of isothermal process, what you know, what is the process equation in isothermal process? Isothermal process also I will consider simultaneously. Isothermal process, in the case of isothermal process, the process equation is PV equal to nRT. In this equation, the temperature is constant and N is a constant, R is a constant, obviously. After differentiating this equation, what do you get? dP into V plus P into dV is equal to, the differentiation of a constant is 0. That implies dP into V is equal to minus P into dV. Now you can write it as dP divided by minus dV by V is called pressure. This is called isothermal bulk modulus. What is it called? This is nothing but called isothermal bulk modulus, right? So let me write the isothermal bulk modulus as B isothermal and this is B adiabatic. Okay, so adiabatic bulk modulus is equal to gamma times isothermal bulk modulus. Okay, and you can see this relation. What is the adiabatic bulk modulus? Adiabatic bulk modulus is gamma P, and isothermal bulk modulus is the pressure itself. Whatever the pressure of the system that is there, that itself is the isothermal bulk modulus, and adiabatic bulk modulus is gamma times more. Okay, this is the adiabatic bulk modulus. Okay, and adiabatic equations into another form also we can take referring to the idea of the fundamental form of adiabatic equation in terms of the pressure and volume is PV power gamma equal to constant. You can say now that same equation I am projecting here, that is P V power gamma equal to constant. I'll take the help of ideal gas equation. What ideal gas equation says? PV equal to nRT, right? And I'm going to replace the pressure now. So instead of the pressure, I can write nRT by V. Okay. So instead of the P, you can write nRT by V into V power gamma is constant, right? The n and t are taken to be constant, and let this constant be mixed up with this constant. Now the equation can be remodified and be written now as, it is written as t into v power gamma minus 1 equal to constant. Okay, it is another form of adiabatic equation. Okay, and also if you want to replace the volume, the same equation I am going to take now from V into V power gamma is equal to constant. I'll take volume now as, I'm going to write the volume as this implies, what is the volume? V equal to N R T by P. Okay, so this is P in terms of volume, this is the volume in terms of the pressure, right? So now I am writing P into, instead of the volume, I am writing nRT by P power gamma equal to constant. Okay, so now here again the constants can be mixed up. Nr power gamma is a constant and this is a constant, and let this constant and this constant by constant is another constant. So now this can be remodified and be written now as into the convenient form as P into P power 1 into P power minus gamma into T power gamma is constant, right? So P power 1 minus gamma into T power gamma is constant. Okay, this is another form, and this form is conveniently be written into another forms as P power 1 minus gamma by gamma into T is constant. This is also the same form, and also as a power of temperature also be written P into T power gamma by 1 minus gamma is also constant. So these are all the various forms of adiabatic equations. Okay, so how this basic and fundamental idea came, and based on the adiabatic process, and how do we go for the other processes and all, we will see in the coming classes. So far as this today's class is concerned, whatever we have discussed so far, we will see in brief as a nutshell the internal energy of a system, the kinetic energy, potential energies we have seen here, and the temperature. The internal energy is a pure function of temperature, and the degree of freedom for different atomic cities we have taken. For monoatomic gas it will be 3, for diatomic gas degree of freedom will be 5, for polyatomic gas it will be 6, and for extraordinary temperatures, so the extraordinary degrees will be taken additionally to one potential and another kinetic, and Cp, Cv, gamma values are taken for different atomicity gases, and the external work calculation we have seen P dV is the external work done, and zeroth law, first law and second law, 3 laws are there. First law of thermodynamics is delta Q equal to delta U plus W, and types of the systems based on the type of the boundary, they are open system, closed system, and isolated system, and the isothermal process temperature is constant and indicating curves, internal energy, and first law of thermodynamics expansion, and it's formulated simplified formula version we have seen here, and the isothermal work done was calculated isobaric process. It is also called volume constant volume process, isobaric pressure process, and P delta V is the work done and its indicator diagrams and various other forms mathematically we have taken, and its specific heat is Cp that was calculated, and isochoric process, a constant volume process, and all the indicator diagrams and all we have taken. It is adiabatic process, isolated system, and adiabatic equations in various forms we have seen, and the very general process of all these processes and followed by second law of thermodynamics we will see in the coming class. Till then, stay connected and do follow all the assignments and stay connected. Make best use of all these sessions. Thank you, one and all.